The amount of memory, RAM, on a typical laptop is probably somewhere between 8 and 128 GB. This is the part that interacts directly with the CPU. Apart from that, your hard drive may also contain, let's say you also have about 1 terabyte of memory. But how much storage is there? In other words, do you have a human brain, and can it be measured in bytes? But maybe it's not the first time questions we should ask. There are many memories in the brain, but where are they located? Because every work computer memory has a physical location. For example, to access a data item in RAM, you need to know the binary his address associated with this location. In fact, this also applies to the CPU. It's important to turn on the right wires precisely to get the bit where you want it. Now, let's imagine a different kind of memory. Instead of specifying an asterisk location asterisk in memory, what if you could specify its binary address, asterisk what asterisk it is, and its contents? Storage system. Providing an incomplete version of memory will cause autocomplete. Of course, with the right software, your computer can already do this, but that's not how computer memory works at a basic level. The purpose of this video is to help autocomplete reminders, also known as asterisk associative memory asterisk. It is a type of natural operation of a network of neurons. This makes it clear that the measurement is meaningless. The storage capacity of a network of neurons is measured in the same way that a computer's memory is measured. The biggest difference is that your computer's memory has locations. Although location is fixed, as we will see later, memories within associative networks tend to have time. Computer memory, in a nutshell, computer memory is measured in bits, or binary switches of 1 and 0. 8 columns. Such bits can represent anything from characters to integers. For our purposes, let's visualize these are patterns of this type, like 64 bits representing her 8x8 image of binary pixels. I always find that there is a missing piece in the story of bits as memories. It is as follows. For example, how can I retrieve memory if it is stored in RAM? Because it doesn't have much effect on its own. It is only useful once you obtain it. So how are we doing? Well, in general, and I won't go into many technical details here, but all data in RAM is mapped to binary files, address. And that binary address ends up being a series of wires. In this case, he has 8, either on or off. Each data resides in a different physical location. You can only access it if you know the address. How to read and write memory. This is actually the core of programming and is a separate story. I want you to remember what was special. The fact is that memories are linked to addresses, and ultimately that is the only way to recall them. Neural network modeling. Compare this to what we believe about the brain. There is no central orchestrator. Like the CPU, it has no address. Instead, for many people, it's a constant hustle and bustle. An independent unit called a neuron. In this video, we will try to understand the hum sound. Neuron network activity by introducing a mathematical model called asterisk Hopfield network asterisk. It was named after the author of this work in 1982. And as much as this has to do with memory, in general, this video is intended for modeling lessons, and I see it all the time. Essential art. This is a neuron. I'm sure you've seen something like this before that, but sometimes it's worth remembering why we always come back to it whenever we understand things about the brain. In my opinion, the reason is that it works very simply. Integrates electrical signals from other neurons to determine its own activity. Send this activity back to the network. Mathematically, the story goes like this. There are electrical signals coming from other neurons, but as we say, they are only a few. The synapse then acts as a multiplier for these signals, another set of numbers. The neuron's activity is based on the weighted sum of its inputs. And that's what we mean by based on. It's okay to calculate the sum and then apply the function. That's all. That'll make it interesting. After creating the network, connect the outputs of neurons to the inputs of other neurons. This is a special type of neural network. This is a asterisk regular network asterisk, and this means that there are forward and backward connections between neurons. But I haven't drawn it yet. Note that each such edge actually consists of 2 edges, so the 2 neurons influence each other. Memory in dynamic systems. Well, we need to explain in detail here, but first, what does this mean? Do you do it from memory? I have no choice, it has to be here somewhere, right? Where? Remember the idea associative memory, the ability of a system to perform a type of pattern auto-completion. Let's try a slightly broader definition of memory than what we're used to. After the storage system is in a certain state, the configuration allows you to return to this state later. Now, our computer memory, including the CPU in the memory system we just talked about, actually has this property. But our network seems different, so let's get creative. There are many other things in our daily life. A life that falls under our definition of memory, and you, and listen to me, can be a simple person, pet bottles. If it crashes, that is, the configuration changes, it may revert. In some cases, it is restored to a previous state and can be thought of as remembered in this sense. And the metaphor is, it's not optional. In fact, I think that's what a network of neurons is. What I want to say is, neural networks are systems with dynamically evolving patterns of activity. If, for some reason, you can build your network to a desired state and return to that state, if this state is destroyed over time, it could reasonably be called memory. This is a network of 64 neurons that I cleverly designed to memorize this 8x8 binary pixel pattern. What happened? To explain what this model actually does, you need to do the following steps. Remember how I said time is of the essence? I need to explain how network activity changes over time. And then there's the problem of asterisk learning asterisk. How do we really engrave our memories on networks? And it will relate to the connection between them neuron. Finally, we need to understand if and when the network converges to a memory state. A key component of our network is the fact that it is a dynamic system. Activities change over time. By activity, we mean each of her 16 neurons in the network. Let's assume that is represented by a number and that this number is a function of time. Time moves in discrete steps. I'm also interested in the state of binary storage. So assume that activity means that the neuron can only be in one of two states, -1 if inactive, +1 if active. In any case, that's all we have left, 16 negative or positive values at any time. This is called the asterisk state asterisk of the network. What would happen if we actually increased the time by one step? Imagine unfolding the time dimension within space. Now randomly select one of the neurons. Updates the state according to the inputs of all other neurons in the network. The remaining neurons remain the same, and we will continue to do so. The remaining neurons remain the same, and we will continue to do so. But wait, you may be wondering how exactly to update the status. And why does he update only one neuron at a time? Now for your second question, you can actually do something like this. We update all neurons at once, but the question here is validity. Because it will require a global update signal, almost like a clock, that tells all neurons to update at the same time. To be honest, it's not too much, but it would be a little more practical to have it updated. Asynchronous. Now, one more question. Yes, what is the actual update equation? Well, it's very simple. This is a weighted sum of the states of other neurons, the weight. This means that each state is multiplied by the strength of the connections between neurons. In this sense, the connection weights the input, so we'll actually do that from now on. We call them weights. Of course, if you want the result to be +1 or -1 again, let's use the function f mentioned earlier. That's all. Anyone who knows linear algebra will recognize this as a computer. Dot product of the vector of neuron states and the vector of connection weights. This is a network of 64 neurons, but I will explain without explaining how. This means that you remember this pattern. Start with various initial states, and then run the equation described earlier and randomly select and update one neuron at a time activity. Wait, let's make it a little easier. You can see that the network is actually active. This attractive property of focusing on memory patterns in all cases, or, well, in some cases, you can end up with anti-memories. Ignore it. It has to do with one. The network has some symmetries. More on this later. Once you settle into this state, that doesn't change anymore. Memory patterns are so-called stable states of the network. So can we be sure this will always happen? No. For example, the situation gets complicated when multiple storage devices are stored on the network. We would get in addition. However, in the simple case of just one storage, the network will be concentrated on one side or the other. Memory or its anti-memory, or as an edge case, becomes completely inactive. So let's summarize again. Learn a network is simply a vector that evolves over time, and its elements are updated asynchronously. Given the foursome weight settings, there is a stable state within the network, which is called a memory state. And although it hasn't been proven, it turns out that networks gravitate towards these states. Questions remain. How can I make the network remember a particular pattern? In other words, how can we design a stable state for the network? This comes down to setting the weights. It turns out that the network is a matrix with as many rows and columns as there are neurons. For example, the state of this neuron is determined by the weight of this row of the matrix. At first, this may seem impossible, especially if you want to store multiple storages on the network. Therefore, I will teach you the rules of magic and then explain. For example, given a desired memory state with 8 elements, look for an 8x8 matrix. Seemingly out of nowhere, the weights I, j between 2 neurons generally become determined by the product of states in memory. For everyone interested in nonlinear things algebra, this means that the matrix is the cross product of the memory vector and itself. Except for the diagonal, we set it to 0 because we don't want self-reinforcement. But why? Think about it this way. In a sense, our whole approach was to make something interesting out of a lot of things. Simple parts. So there must actually be a way for 2 neurons to determine the weight between them. They operate independently from the rest of the network. This is a principle called Hebbian learning, and it's very plausible. Because remember how weights are supposed to be synapses? And the synapses of actual neurons also have no way of knowing what's happening in the broader network. So why multiplication? Now, this is why we coded the binary state -1 and +1. If we map all her 4-state combinations of neurons, we find if the memory states of the neurons match, the weights have a positive sign and negative sign. If they don't agree, this should make sense since positive weights create a project of neurons. Its state is sent to other neurons, and using negative weights allows a neuron to reverse the state of other neurons. It's as if neurons behave like charged particles, perhaps? One last question. You can see it in action, but the question is, how can I store multiple patterns on the same network at the same time? This is done by calculating the cross product of all required memory patterns. This will give you a matrix. Average these matrices for each. This provides even more granular weight tiers. Here, things get a little more complicated. There is no way to guarantee that all memory patterns are stable. It's frustrating when memories start to talk to each other and blend into new memories. And at the same time, very interesting. Here we also have a network with 4 memories. It's sometimes, yes, it converges to one of the memory states, but it converges to something else. I think the fusion of memories in between is mostly a type of human error. So I'll finally take the question from the beginning a little further. Start a video. How much memory do you have? Originally, you could answer this like this. You specify a specific number of bytes, but the problem is completely different. It's something like this. How many memory patterns can be stored in this way in a recurrent network of a given size? Is the network stable? And at least when it comes to this model, the answer is not very much. Memory capacity and conclusion. The original paper shows that this model only has linear storage capacity. It's called a number. The number of stable states increases as a linear function of the size of the network. There are hidden things. This diagram assumes that all memory states for any set are uncorrelated. Images like this are definitely not applicable. I've picked out some things that don't fit well. The photo really shows what you can do with this network, and the results, see for yourself. Realistically, This means that this model may end up being too simple, but that's not surprising, given all the violence we have done to these networks through many simplifications. But the goal is, you don't need to watch this video to convince yourself that this model is practical anyway. However, in a follow-up video, I would like to explain what steps people took to create this model. In fact, it is useful for deep neural networks. Here's what I wanted to accomplish with this video. I caution you against making false comparisons. Neural networks don't work like USB sticks, and why should you? But secondly, it shows how a modeling approach can be used to take a very big step forward. Sometimes we can begin to imagine the world on the fine line between complexity and simplicity. It's different than if it wasn't. Perhaps you have ever imagined the concept of memories as something it's static, but I hope you're now ready to consider that it can be dynamic.